Chapter 2 is really about descriptive statistics. Now this is how we organize and we graph data so that it paints a picture, so that it gives us a true glimpse at the meaning behind the numbers. The first two terms you're going to want to jot down in your guided notes are bar graph and Pareto chart. Now, these are graphical presentations. In this particular case, the data is qualitative data. In other words, these are groups of items. The first one is ethnicity of students, so they're grouped into category by their ethnicity. And then you see how many fell into that category. That's the height of the bar. That's the frequency, the height of the bar. Now, this bar could have been, it is a vertical bar. It could have been a horizontal bar. It still would have been a bar graph. The only difference in the bar graph that you see at the top and the Pareto chart that you see at the bottom is that the Pareto chart is sorted so that the most highest category is first. In other words, the highest frequency, or the one that had the highest percentage of the students in it, is listed first, and then it's in descending order all the way from left to right. Now next we have what we call a pie chart. Of course, this is just a circular representation of a bar graph. If you look at the pie chart on the left, you're going to see that it is a little bit more confusing than the one on the right. That's because the one on the right is sorted according to the sizes of the categories of the different groups. And that makes it easier for us to read, easier for us to interpret, and easier for people to understand. Next is a histogram. Now this is a graphical display of data. It uses bars of different heights again. So the frequency is represented by the bars, the height of the bars, but notice there's no space between them. So this histogram, it really displays the shape of the data, and this is used for continuous sample data. In other words, when it's quantitative data, but it's quantitative continuous data, this would be used for a better representation of that. If we take it a step further, what we have is a polygon. Now, a polygon is really just having the midpoint in the top of each of the bars of a histogram connected. So we would say this is just the shape of the top of the histogram, so to speak. We're going to deal a lot with a lot of histograms in this course, and so you need to get familiar with their shapes, and there's some very important facts about the shapes for you to remember. The top one we're looking at is called a symmetric histogram, and that means that if you folded it in half, both of the sides would match. It would be exactly the same on the left as it was on the right. It is a perfect uniform shape. That's a symmetric histogram. The two bottom ones are skewed. Now, skewed means the data is either shifted to the left or it's shifted to the right. What you need to remember is that the skew is where the tail, the small part of the histogram is. So if we look at the one down on the bottom left, it's actually a left skewed histogram. That means that the tail of it, the smaller portions, the smaller bars, are on the left side. The right skewed histogram, smaller bars, are on the right side. That's the skew of the histogram. So wherever the skew is, that's where the tail of the histogram resides. Let's do an activity on page 4 of your guided notes now and see if you can label these four curves at the top. They're either symmetric or they're skewed to the right or skewed to the left. Why don't you stop the tape for just a second, label those four curves, and then start back. Now the first two that we have at the top are symmetric. You can see this test for symmetry is if you can fold the curve in half, both sides match. Even this sort of odd one, curve B, is really symmetric because it's exactly the same on the right and the left. It's an identical curve. Now down here, curve C, of course, has the skew, which is the tail of it, is over here on the right. So this is what we call a right skew. And the curve D on the other side has the tail on the left, so we're going to call that one a left skew. As you've been able to tell probably from reading Chapter 1 or looking into what we've done in Chapter 1 and now in Chapter 2, statistics are everywhere. Quite often they're reported and used by reporters or people who want to prove a point. They might change the statistics or the numbers just a little bit. Even if they don't change the numbers, they can use a couple of things that make it look like they've made their point. And this is something that we call, I've given some illustrations here of two of those cases. Basically, both of them are truncating the axes of the graphs, of the histogram graphs. Now, the first one is called changing the scale. Now, you can change the scale either on one or both of the axes, and that means you either stretch it or shorten them, and it makes the chart look like it's saying something that it's not really saying. The other thing you do is truncate the frequency axis. That's the starting point. If it's bigger than 0, you know you're not seeing all of the data when the starting point is not at 0. Take a look at these two graphs that are on this page. You might want to make a note on some of it on your page, on the ones I've given for you to write on in your guided notes. This one, the first one, starts at 0 and it goes up in the same incremental units, and it's a really good representation of the data. The average for these four, I don't know if it's average height or average whatever, but average for these four students, maybe, there it is. Okay, now we've taken the same data and we've done something called truncate the frequency axis. In other words, it doesn't start at 0 anymore, it starts at 1. And the increments are now greater that are going up this scale. They're really quite different. Look, it still just ends at 2, doesn't it? So what has happened? Well, basically, they've cut this chart off right here, right at 1, and Leah is not even included in the new graph. It looks like she has nothing, no size at all, right? Look at the difference now in Gordon and Katha, or Katha and Sophie. It looks like there's a huge difference in size. Whereas if you look at the realistic data, not so great a difference at all. So if you were trying to make a point or trying to prove that something was tremendously greater than, better than, higher than something else, and you wanted to stretch the data, you could do something like this. However, it's highly unethical and not very honest. So you have to watch when you're looking at statistics to see what people have done and if they've truly represented the data. Another type of graphical representation of data, which really doesn't even look like a graph to us, but it is called a stem and leaf graph. Now, this really comes from exploratory data analysis, and it's a good choice if you have a small data set to do a stem and leaf graph. And if you look at this one I've got illustrated here, you can see that I've divided it into, they are really 2-digit numbers, well, maybe 3-digit numbers when you get to the final one, but basically 2-digit numbers. The first digit of the number becomes our stem, and the second becomes the leaf. Now, one stem can have many leaves. We notice that we start with a stem of 3, and we go all the way up to a stem of 10. We don't want to skip any stems in there. Even if there are no leaves on the stem, we still want that representation to show the gap in the data. Leaves, there might be more than one of them. So, for instance, how many 40s are there? Well, there was a 42 and 2 49s. So we did put 49, we put 2 9s down there to show that there were 2 49s. Now, this data set has already been ranked. In other words, the leaves are written in ascending order. But that's not the way you would normally write it the first time through. The first time you were just gathering stem and leaf data, you might just write down leaves at random and then go back later and organize them so they're from smallest to largest. Pretend, for example, that this is a group of test grades. And I look at it and I say, okay, well, the lowest score in my class was a 33 and the highest was 100. How many did I have in the 90s? Well, there were quite a few in the 90s. In fact, that was the highest class, highest group, except for the 60s. So where did most of my students score? Well, in the 60s or the 90s. And that kind of is the way the stem and leaf graph actually works. You can see the numbers are written in the same distance from each other, so it sort of does form a graphical picture. The other thing a stem and leaf graph does for us is it doesn't lose any of the details of the data. If I had this stem and leaf graph over here, I could go back and I could create all of the raw data items, all of the individual scores of Susan Dean's pre-calculus class could be created. I could look at it and I could say, okay, I can list all of the test scores. I had a 33, a 42, 49, 49, 53, 55, 55, and I could list every score. I haven't lost anything. Notice that's not usually true of bar graphs. When we put something into a group in a bar graph, we don't know how many, really we've lost the individuality of each of those items. We know they go into the group, like I know that these are all scores in the 60s, but I don't know how many scored 68 or 69 or 61. In a stem and leaf graph, I haven't lost any of the details, and that's one of the advantages for using a stem and leaf display that you might want to write down. You do not lose the detail in the data. Now you can also kind of tell what's going on with the data very easily at a glance, just like any other graph. You could say, 8 out of the 31 scores were 26% higher. We're in the 90s and hundreds, and that's a pretty good number of A's there, and that helps me to analyze my data. So it's a very good graphical representation if you have a small group of data. There's an activity at the bottom of page 5 I want to start with you, and it's basically a group of raw data that I've given you. They're multi-digit numbers, and I want to do 2 graphs, 2 stem and leaf displays. First one is unranked. Now that means we're not going to write the leaves in any certain order, just however we come to them in the data set. The second one is going to be a ranked stem and leaf display. So I look at my data first, and it has 3-digit and 4-digit numbers. So I'm basically going to say, okay, I want to split them in half. I'm going to create 2 digits where there aren't 2 digits. In other words, for a 9, I'm going to call that a 09. So I'm going to split these into, this is 9s. Do I have anything smaller than 9s? Well, I have 6s, and I keep going across. Do I have anything smaller than 6s? Well, looks like I'm going to start with a stem of 6. That's going to be my smallest stem. Now, what's my biggest stem going to be? Look at the first 2 digits and see we have 11s here, we have 12s, 10s. It looks like I'm going to go all the way up to 12. So I need 6, 7, 8, 9, 10, 11, and 12. Those are going to be my stems. Those are my groups. I'm going to throw my data into these groups. It doesn't matter the order that I put them in, because I'm going to order it later when I rank the stem and leaf display. First thing I do is I look at the first one and say it's a 9. It goes in this group 9, and it has 2 digits behind it. That's an 80. Now I'm going to have to be careful to put some space between them because these are 2-digit stems, right? The second one is 1215. So I'll come down here to the 12 and put a 15 by it. The third one is going to be 1181. Got one here, 995. And I'm putting some space just so that I can tell those are separate numbers, separate stems. 621, 1235, 1075, 935. Like I said, it didn't matter if I went straight up and down with these or across. It's just what order you put them in doesn't matter at first. 1223, 855, 765, 845, and 1135 is next, and finally 1100. Now those are zeros, but it still represents a basic data item, so I've got to put it down. Now I've got my data, let's go ahead and rank it. In other words, we're going to create another stem and leaf display. Same stems. I'm going to go from 6 all the way to 12. And I'm going to take each group of leaves and I'm going to put them in ascending order. Well, I just have 621 here. I only have 1 on 7. And I need to reverse those 2 on 8 and make it 45, 55. On 9, I want to start with the smallest one. I want 35 to come first, and then 80, and then 95. 10 only has 1. 11, I'm going to start with the zeros. Then I'll put 35 and 81. 12, I'm going to do 15, 23, and 35. Difference in an unranked stem display and a ranked stem display. Now let's talk about another type of graph called a dot plot. Now a dot plot is really a number line, and the data was represented as dots or points above the number line. This dot plot has a particular value to us. It tells us very small or very large data values in relation to the other data set. In other words, if something is so much bigger than the others that it really can't relate to well, we would call that an outlier, or it could be so much smaller than the other items in our data set. And a dot plot would help us to identify that. Now let's use this one for an example. On page 6, you can recreate this dot plot that I've got on the screen. Using the data points 5, 5.5, 6, 6, 6, 6.5, you get the picture. That's the data. It was a statistics class that was polled to ask the number of hours they spent sleeping each night. Now what I do is I set up first my number line. I have the smallest number I have need to represent is 5, and the largest that I need to represent is 9. Fortunately, my data has already been ranked smallest to largest. That helps me. And so I can now say how I can start filling in the dots. I'm drawing circles. You can just draw colored dots if you want to. But over the 5, we just have 1. Then there's a 5.5. Well, I'll just go halfway between the 5 and the 6. When I have 3 6s, I'll stack them up. And 4 6.5s, I'll stack those up. 2 7s, 2 8s, and a 9. And you can sort of see, now this is truly probably the 9 is much further away from the other data items, but not too far actually. So we don't have anything that we would really consider a true outlier. But the 9 would come as close as we've got to anything as being farther away from the other data items. A dot plot would show us, though, if we had somebody who slept 15 hours a night, for example, it would be way out here on the right, and you would see it was a lot further from our other data set. For the question you have at the bottom of page 6, consider this. How many of the 14 students slept between 6 and 7 hours a night? We'll count them. 6 is 1, 2, 3. There's 6.5, 4 of those. So far I've got 7. On 7 hours a night, I've got 2 more, so I have 9 out of 14. If I want to see what percentage that is, I take 9 and divide it by 14. I come up with about 64%. It's 0.642, I think, and you would round that, or you would just say that's 64% once you convert it into a percentage. We could also look at that 9 hours per night and say it's really far away from that center of our data set, pretty far away, and we could call that an outlier, although technically it might not be. Now let's go on and discuss something that you're more familiar with probably, and these are measures of center. We call them measures of central tendency. Measures of central tendency, or the measures of the center of the data set, are the ones that we use to identify the middlemost values. Now, there are 3 different common measures that we use: the mean, the median, and the mode. And I'm sure that you are familiar with all 3 of those. We need to also be familiar with the relationship between the mean and the median and the mode in our data sets. First, we're going to discuss the mean for ungrouped data. Now, the mean for ungrouped data is found by dividing the sum of all the values in a data set by the number of values in the data set. We can be dealing with 2 different types of data: population data or sample data. The formulas may be different for population and sample data, so it's important for us to make that distinction early. First, we have a symbol. That little funky looking U is really called, it's a Greek letter mu, and we call that the population mean. Every time you see that, it's representing the population mean. It's equal to the sum of all the x values divided by capital N, which represents the population number of data items, number of items in a population, capital N. When we're dealing with sample data, we have an x with a bar over it, which we call x bar. So that sample mean, or x bar, is always equal to, once again, the sum of the x values, this time divided by the number of items in the sample. Basically, those are the same formula, aren't they? But it's important later on when we are calculating other things that we recognize what type of data we're dealing with, population or sample. That's why we use the 2 different symbols. Here's a real quick example of calculating the mean, and like I said, it'd be calculated the same if it was a population data or sample. The mean is basically calculated the same way. You take all of the items that you have in the data set, you add them up, you divide by the total number of items in the data set. For this one, we're saying it's a sample of data. We add them up and we divide by the number of items in the sample, or 11, and we come up with 2.7 is our mean. And you could also call that the average. Now we want to consider what things like outliers, how they affect our measures of central tendency. That's very important to us, because if we have outliers in our data set, the measures of central tendency could not be telling the true story. So this is an example that has 8 homes that are for sale in a city, and you can see that one of them is really a lot more expensive, or it's worth a lot more than the others. So that home that's worth in the millions, when the others don't even come up to $500,000, would be considered an outlier. This one is so much larger than the others that it's going to affect the data. It's going to move some numbers around. It's going to make the data set as a whole look different. So we want to see how this affects the mean, the measure of central tendency called the mean or the average. Now I have an example for you, or something on page 8 that I want you to do. And the first thing I want you to do is to calculate the mean with the outlier. In other words, add all 8 of those homes up, add all those price values or prices together, and then divide it by the number 8 and see what you come up with. Do that right now. Next, I want you to do step 2, calculate the mean without the outlier. Now, what are you going to do? Well, you're just going to not add the 8th house together. You're going to add 7 of them. You're not going to divide by 8 this time, because you're only adding 7 numbers together. So it's changed your data set a little bit, but see what that data set looks like if it didn't have an outlier in it, and see what your mean comes up to be. Now, explain the difference to me. What did the outlier do to the mean? Here's what I found when I did the calculations. I'm looking at the mean without the outlier first. So I took the 7 houses and added them together, and I came up with an average price, or a mean, of $315,536.29. That was the mean of my houses. Now when I look at that data in my relation to the prices of the data set, I say, yeah, that looks pretty much like the average of those 7 houses. But here's what happened when I included the outlier. The mean with the outlier, the average price of the house went up considerably. It went from a little over $315,500 to $760. It more than doubled as the average price of the houses. Now, that means that the outlier has done something to the mean. It has skewed the mean. Make a note. The outliers will skew the mean in their direction. In other words, they will pull the mean toward them. This is a very important concept for you to write down on that page 8. Outliers will pull the mean toward them. In other words, if the outlier is a lot larger than everything else in the data set, it's going to make the mean larger. If it was a lot smaller, like I had a house in that group that was in a foreclosure for $50,000, it would make the mean a lot smaller. It doesn't mean that we don't include outliers in our data set, but we do need to understand what they're doing to our data and make an intelligent decision based on that understanding. Our second measure of central tendency that's fairly easy to understand, this one is called the median. Now the median is the value that divides a data set into 2 pieces or 2 halves, but particularly note that that data set has to first be ranked in order from the smallest value to the largest value. So you first have to have an ordered or ranked data set, and then you split it into the data item that splits it into 2 pieces is the median. But what if you have an even number? Well, if you have an even number, you take the 2 middle values of the data set and you average them. You add them together and divide by 2. Just to reiterate that point, these are the steps for calculating the median. First, you rank the data set in increasing order. This is the step, as easy as it seems, this is the step that most people will miss on the test. Rank the data set first. Next, find the value that divides it into 2 equal parts. That value is the median. If it has an odd number of data items, well, it's just the middle value of your data set. The middle one is the median. But if it has an even number of observations, then you find the two middle values and add them together and divide by 2, or get the average of the two middle values. I've given you an example here and a chance to try calculating the mean and the median for this data. Now, I've already ranked this data in ascending order, so that part's already done for you. This is actual AIDS data taken, and it's a number of months that AIDS patients were given to live after taking a new antibody drug, and it's ranked in from smallest to largest. And what I want you to do is take that data and first calculate the mean and then calculate the median, and then start your tape back. Now, what I found when I did the calculations was the mean was 23.575. I went ahead and didn't round it, just gave all the decimals I had. And the median was actually right between 24 and 24. So it was an even number. It was 40 items, so I took the 20 and 21st item. They're the same thing, so 24 plus 24 divided by 2, of course, is 24. What is the advantage of using the median? Now, the median, I will tell you this, is sort of a different type of a measure of center of the data set. It does have the advantage that it's not influenced by outliers. If one of these items was extremely large, let's say this one was a 99, it wouldn't affect the median at all, would it? And so the median is really not influenced by outliers. So if your data set has outliers in it, then the median might be preferred over the mean, and that's important for you to remember. The third measure of central tendency that we are responsible for is the mode. Now, the mode is the value that occurs the most frequently in a data set. If you have a data set and it has two numbers that are the same and all the other numbers are different, well, that one that had the two matching numbers, that would be your mode. Now, there are some disadvantages to the mode. First of all, there can be one mode, or you might have a data set that actually has two modes in it. We would call it bimodal. You could actually have a data set that had 3 modes or 4 modes or 5 modes. It really is as high as your data items go. That would be a multimodal data set. And then you could possibly have no mode at all, one that every data item was unique or individual. So the mode is not really too reliable, and it's probably our least used measure of central tendency. Let's see if you can find the mode, and once again I've ranked this data set so that you can look at it and easily tell. See if you can find the mode for these exam scores of these 20 students. As you can see, you probably found it pretty quickly. There's one score that pops up more than any other, and that's the score 72. 5 of the students scored 72. I think that's 5 of them. And nobody else had 5 matching. I didn't have anybody else that scored the same thing, or 5 people that scored the same thing. So that would be our mode. Now, take a look at this one more time with me. What are the advantages to using the mode? Well, the advantage to using the mode is that it's easy to calculate. The mode is simple to calculate. There's not really anything we do. It's just a glance at the data. That's one advantage to using it. What are the disadvantages? Like I've told you, it's not as reliable. There can be one mode, or there might be multi-modes. There might not be a mode at all. So those definitely are disadvantages. And that's one of the reasons it's not as descriptive of our data, so it doesn't tell us too much about our data, and we have a tendency not to use it much as a measure of central tendency. Now I want to show you some ways you can use your calculator, graphing calculator, to do some of these calculations as we go. So I'm going to be working with a TI-84. If yours is not, in TI-83 works basically the same way. But other calculators, you might have to Google how to do a measure of central tendency with whatever your type of calculator is, and it'll be able to tell you. Somebody out there has put a YouTube video together, I can guarantee it. First, let's take a look at our data set. And the first thing I've got is I have the data set that I think we had used on our previous page, and I've entered it in a list. To enter a list in your calculator, you first see the list button right here above the stat. Well, I'm going to hit the stat, and then I'm going to say edit. I want to edit my list. That's number 1. And it brings up a bunch of lists, and you can put data in any, and I've been working with some problems, so I've got data in list 1, 2, 3, 4, but I had entered the data that we're talking about into list 5 over here. I don't know if you can see that, but that's list 5, okay? So I enter my data into list 5, and after I enter a value, I press enter, and then it goes down to the next value. You just have to make sure that you enter it all correctly in there. Let me just show you how we would do a list of data here. I'm going to take the data set that's listed on this page, and I'm going to say enter 50, and I hit enter, and it goes down to the next data item, and then 53, and 59, another 59, 63, another 63. I've got 5 72s. I've got a 76, 78, 81, 83, 84, 3 of those, a 90, a 93. I think I got them all right. There were 20 of those. And look, it says I'm on number 21 over here is what it says in the corner, the left corner, and 21 is blank. So I've entered 20 of them. I would usually go and do a real quick check. I'm arrowing up just so that I can look at that list and see if I entered those numbers correctly. But that has my data set has been entered into list 6 here. So now I want to go to do the next step of it. I want to go to stat again. So I'm going to hit the stat button. And this time I'm going to move over to where it says calc. And I want to calculate one variable statistics. Now, if, like I said, you're not working with a TI-80 whatever, then you might want to say, Google, how to calculate one variable statistics with a whatever type of calculator yours is. And let's hit enter. My calculator comes up and asks me, which list do you want to use? Well, for the last problem I worked, I used list 5, but I'm going to change that to list 6. Now, list 6 is an L6. It's the blue right above the number 6. So I have to hit the blue shift button here, second, and then I'll do 6, and it'll enter list 6. For this type of calculation, we're not using a frequency list. This is not grouped data, for example. This is not grouped data. We'll use frequency list later. And so I'm skipping down on that one. I'm just going to skip it, and then I'm going to say calculate. It takes that list 6 that I entered, and it does some calculations. It tells me the mean, the average, okay? Now, it uses X bar. It doesn't know whether it's dealing with sample data or population data, so it doesn't use the mu signal or symbol. It just uses X bar for mean, and you have to know whether you're dealing with population or sample. It tells me the sum of all the X values. You know, you were adding up values of X, and you might have that, might be a useful thing for you to put them in a list and let it do it for you. It tells me the sum of all the X values squared. Remember that calculation that you've been doing? Now, the next two we'll skip over. Those are standard deviation. We'll talk about them later. It tells you how many items are in your data set. Once again, it doesn't know if it's population or sample, so it just uses the little n. And then it tells me the smallest value was a 50, and then it does something else. Let's scroll down here a little bit. It tells me something called a quartile 1 and quartile 3, and then it hits something that I understand, the median. There's the median of my data set. It's 72. So it's giving me minimum values, maximum values, quartiles, which we'll get into later, and the median. It also gives me the mean. So you can use this. You can use list and one variable statistics calculations to calculate your mean and to find your median of your data set. Here's the steps if you want to jot them down. First, you enter the data into a list, you hit stat, and then you say edit list whatever. List 1 is where you can put it. I put it in list 6 in our example. And the second thing you do is you calculate. Once again, you hit the stat button, you go to the calc menu, and you choose one variable statistics and hit enter. Page 11 is an activity for you to do on your own. I've given you a data set that belongs to a population. So I want you to calculate this population data. Be sure you use the correct symbol for the mean and calculate the mean, the median, and the mode. Find the mode of that data set. Example 2, I've got a sample data. Be sure you use the correct symbol for the sample mean. Calculate the mean, median, and mode again. And for example 3, I want the measures of central tendency for this data set, the mean, median, and mode, and you might want to use a list for it. Now notice, this is in 4 columns just to save space. If you enter this data into a list, it all goes into the same list column. It'll be a very, very long list, but it all will need to be in the same list. Look for these answers to be posted later. Now here's some important concepts that you need to understand about the mean, the median, and the mode, and skewed data. First, let's talk about a symmetric histogram. That's that histogram that is exactly the same on the right and the left side. In a symmetric histogram, it's something called a normal distribution. We call that a normal or a standard distribution. And the mean, the median, and the mode are all the same. They're exactly in the center of that histogram. They are the same number. I'm sorry, that line might not be drawn completely in the center, but the goal was to put it in the middle of that histogram. That's a normal distribution. That's a symmetric histogram. Now, if the data is skewed to the left, what happens? First of all, what happens to the median? It really basically stays the same. You can think about the median as the middle. It's always going to be in the middle, okay? So the median kind of stays the same. The mode goes where the most values or the data are, so it goes to the highest point of the histogram, and the mean is pulled toward the skew. Remember our illustration earlier. The mean is always, the average is always going to be affected by the skew of the data. The mean is going to be pulled toward the skew. The same thing happened in a right skewed histogram. Median stays in the middle, mode goes to the highest point, and the mean gets pulled again toward the skew of that histogram. These are things that you want to remember because you're going to be asked how the skew of the data is affected, how the mean is affected by the skew of the data. The next measurements about data that we need to discuss are called measures of dispersion, and we're still talking about ungrouped data, although we do have the same terms for grouped data, but let's just for now consider ungrouped data. The measures of dispersion are basically statistics that tell you how similar a set of scores are to each other, and dispersion is really a way that we talk about how spread out the data is. So when a data set has a very large spread, then the values in the set can be widely scattered from each other. When it has a small spread, that means the data set is the values are more tightly clustered together. For example, if you had the first data set I show you here, 1, 2, 2, 3, 3, 4, well, the range is only from 1 to 4. It's a really tightly made data set. But if we go from 0 to 100, well, those may be a little more spread out, and you can see the individual data items are more spread out. So we have 3 different measures of dispersion that you will be responsible for, and they are range, variance, and standard deviation. The easiest one for us to talk about is the range. Now, the spread of the data, just like we've looked at on the previous slide, is really the range. The range is the largest value of the data set minus the smallest value. Now, as you can tell, it's only calculated on 2 values, the largest and smallest, so everything else is ignored when you talk about the range. That doesn't tell you too much about the data set in itself, so it's not really a very satisfactory measure of dispersion, but it does give us some information. It is also dependent on outliers. It can be very influenced by outliers. You can imagine that if we had a really high value in our data set or a really small value, it would definitely affect the range. So we call this a non-resistant measure of dispersion. It does not resist the effect of the outliers. The next 2 measures of dispersion sort of work together. They are the variance and the standard deviation. You'll see what I mean in just a few minutes when we start looking at the formulas, but basically we have to calculate the variance to get to the standard deviation. But the standard deviation is the measure of dispersion that is the most valuable to us. So what does it tell us? Well, the standard deviation tells us the overall distance or deviation that each data item takes from the mean of the data set. So, for example, we have this set of numbers. They're ages of close friends of Jasmine, and the average, the mean of those ages is 41.5. Now, each of the friends is either older or younger than that average, but how much older or younger from the mean age are they? So we can calculate a number that gives us an overall deviation from the mean. Now, if you wanted each deviation from the mean, if you wanted to take how far it deviates from the mean, you could take 41 and subtract 41.5, and you would see the distance of each one, 38 minus 41.5, 39 minus 41.5. You could see each one how far it deviated from the mean. But what the standard deviation is requires us to take a rather complex formula to calculate. Let's go back and do that again the way that I was talking about it, and just say how much each age deviates from that mean of 41.5. I would take the ages, and I've listed them there, 41, 38, 39, 45, and then I would subtract the mean from those ages. Now, some of these are going to be negative and some of them are going to be positive. And when I take the distance or the difference in the mean and the age, and I add all of those deviations up, the sum of them is always going to be 0. Well, that doesn't tell us very much. If every data set, the sum of all of the deviations of every data set is going to equal 0, we don't have a standard deviation that we're dealing with. So how do we calculate it? How we remedy this is we square the deviations, or we take the absolute value of them to make them all positive. And then we'll square the deviations, and then we'll add them together. So we had a deviation of a negative 0.5. Well, negative 0.5 squared is still a positive number. So we've got a distance of 0.25, which was squared. When we add all of those together, the next step is to divide by the total number in the data set. Once we do that, we call this result the variance of the ages. So we did make it to the variance by doing that. So what we've got is 8.85, which is the overall measure of square ages of Jasmine's friends, and that's what we call the variance. But when you think about it, square ages doesn't make any sense. So what we do now is take the square root of it so we can get back to the original unit that we're working with, which is just age. The result of this is called the standard deviation of the ages, and that gives us a standard deviation of 2.97. So here's the formulas we've been working with. Now that symbol, the little circle thing, squared, is really what we call the variance, and S of the population, and S squared would be the variance of the sample. So we have differences between our formulas this time for variance and standard deviation based on whether we're dealing with sample or population data. Remember, I told you that was going to happen to us, okay? So the first thing we look at is, okay, well, we could take every data item and we can take that data item, subtract the mean, and we can take that difference and square it, and then divide by the number in the population. Or if it's a sample, we have to adjust. So we take the number in the sample and subtract 1 from it. That's where the formulas differ. And then we would have our variance. And how do you get the standard deviation? Well, then you take the square root of whatever that number was, and you have your standard deviation. It's a little cumbersome, though, to take each individual data item and subtract the mean from it, and then take that result and square it. In fact, with huge data sets, it can get really cumbersome. And so we have a shortcut that we're going to work with. These are your shortcut formulas for variance and standard deviation that you're going to use. You might want to circle those on page 15 of your guided notes, and note where they are in your formula sheet while you're at it too, because you'll be able to use the formula sheets on your test. Now, all we've done here is we've got some of those summation notations that we've used in the previous lessons. We've got some of those listed here. In other words, what am I going to have to do to get the variance? Well, I'm going to sum all of the x squared values. And then I'm going to subtract the sum of x squared divided by either n. Well, it's going to be always n. It's going to be either the population n or the sample n. And then I'll take that and I'll divide by either, for population data, I'll divide by the number in the population. For sample data, I will make my adjustment and divide it by n minus 1. After that, how do I get the standard deviation? Simply take the square root of those variance numbers to get there. So let's go through an exercise where we take a small data set and we calculate the variance, and then from that we calculate the standard deviation. the first things you're going to need to do are look at your formulas. Remember the formulas in your formula sheet and back on the previous page, and find that formula for the calculation of the variance. We have to get to the variance before we can get to the standard deviation. And then what we're going to do is find the different pieces of it and figure out what you need to calculate from this data set. Now, this data set is compensations of 11 CEOs of American companies. So these are the salary in millions of dollars of the CEOs of these different companies. Let's do this one together. So let's do page 16 together. Now, the first thing you have to do is we have to identify what we're dealing with, and I want to make a note here. There's a mistake on your page. If I haven't corrected it in your book, correct it. There are only 10 CEOs of these American companies. The first thing we have to do when we're calculating variance and standard deviation is decide, are we dealing with population or sample data? Since there are definitely more than 10 CEOs of American companies, we can assume that this is a sample that has been taken. Now that does matter because our formulas are different for samples and populations. Now we've been given the salaries of these CEOs, which we can identify as our X values. And if we look at our formulas, and I've written them down here for you again, you will note they're in your formula sheet. We want the variance formula, which is our complicated one. And we take that when we're dealing with a sample variance, so it's S squared. It's equal to the sum of all the X squared values minus the sum of the X values squared over the sample size divided by the sample size minus 1. So let's do some calculations. It's sort of written up here what you need. You need the sum of X, and then you need the sum of X squares, and then you need to take the sum of X that you calculated here and square it. If I'm writing that down, I'm going to say, okay, this column right here is going to give me the sum of the X values. All I have to do is add those together. How do I get the sum of the X squares? Well, I'm going to have to come up with a column that says, here are my X squares, and then I'll come down here at the bottom and I will sum those X squared values and be written here. Now I've already done this math for you, but I want you to go ahead and stop this tape and get me those two values before you continue. So, check your work with me. As you can see, I've squared each of the salaries, and then I've added those squares together, summed them together. I've also added all the salaries together. So I have the sum of X, and I have the sum of X squared. Now I need to calculate one more thing. I need to take the sum of X and calculate the sum of X squared. So I'm going to say, if I take that sum of X value and I square it, what I'm really doing here is taking 1582.7 and squaring that. So I need another number for this. It comes out to be, let's see, I've got it written down here somewhere, 2504939.29. Okay, so these are getting to be really large numbers that we're dealing with. Just be careful, watch your decimals and everything. All right, next thing I'm going to do is plug these into my formula. Now I've got the variance formula. The variance has to be calculated before I just take the square root to get the standard deviation. So let's plug the numbers in. What's the sum of X squared? Well, the sum of X squared is this 420,838.03. And then I'm going to subtract, and I'm going to make this a fraction. What I've got to subtract is the sum of X squared. Now the sum of X squared is right here. I did it last. It's 2504939.29. And then I have to divide it by n. That's the sample size. There were 10 in my sample. And then I take this entire thing and I divide by n minus 1. That's when I make the adjustment for a sample. If it was population data, I would simply divide by 10 again. Please keep that in mind because it will make you off and you'll miss the answers. All right, when I do this calculation, I do all the division. And remember, your order of operations with your calculator is sort of tricky. If you try to type all this in and you do it in one step in your calculator, you'll get the wrong answer. You need to work the numerator first and then get your result and then divide by the denominator here. And here I'm going to go through that real quick with you and show you what it looks like. So what I have to do is say 420,838.03, and then I say minus 2504939.29 divided by 10. At this point, order of operations is working in our favor. The calculator will do this division, and then it'll do the subtraction, and that's what we want it to do. If we went ahead and put in divided by 9, well, it would do this division, and then it would do the fraction divided by the 9, and then it would do the subtraction, and that won't work. So we say enter, and we then say divided by 9. And it gives us the answer that we are looking for here. So I'll go ahead and put my answer down here. What did I get for my variance? I got 18927.12233. And of course that would be salary squared, right? How do I get the standard deviation? I simply take that number and take the square root of it. And decimals, we'll just leave them all there for the time being. So I'm going to go to my calculator and say square root of 18927.12233 and see if I entered it right. This gives me a standard deviation of 137.5758747. What is it, 784? Okay, and this is dollars. So I'm really going to say I have a standard deviation of approximately 137.58, and it's in millions of dollars, right? Millions of dollars, because it's in the same units as my problem. Now, that is a lot of calculations to do. And you can shortcut this, or you can use your calculator to do a lot of this work for you. I'm going to show you how to do that. I think I've already talked about it a little bit. It's done with a list. So let's go into our list. And I've done, for my calc for TI-84, I'm going to hit Stat, and then I'm going to say Edit. And I'm going to work in list 1. Now, in list 1, you can see I've already put the X values, the salaries in there, and I checked them to make sure that they're all 10 are entered correctly. So I'm working on list 1 here. And the next thing I do is do Stat, the same thing we did before, run over and do Calc and one variable statistics. It's going to ask me which list, and I'm going to choose list 1, no frequency list, because this is not grouped data. And there are my statistics. Now, it tells me a lot. It tells me the mean, and it is 158.27. Well, nobody really asked the mean, but there it is. It tells me the sum of the X values, 1582.7, and that is the number I got too. And then it tells me the sum of the X squares. Well, 420.838.03. Well, that's this one, and that's a lot less trouble than taking each of these values, squaring it, and adding them together. If I just use my list, it works out pretty well. And then it tells me the standard deviation. Now, it knows that sample and population standard deviations are different, so it calculates both of them. I'm dealing with sample data, so that is my sample standard deviation, 137.578785, and that is exactly what I got when I did the calculation, isn't it? So it calculated my standard deviation. Where is the variance? It doesn't calculate the variance. The calculator pretty much knows that the variance is not something that we use. Statistically, we just use it to get to the standard deviation. But if you wanted the variance, you would simply take this number, the standard deviation, and square it, and get back to our variance here. Now, page 17, I've given you an on-your-own activity, and basically you're going to take a smaller data set and you're going to do the exact same thing. Find the range, the variance, and the standard deviation of this data set. I don't mind if you use your TI calculators to do this, your graphic calculators if you want to, but you do need to find out a way that you can do this so that you'll be ready for the test, okay? I've given you that. And I've also told you with this very large data set, I would definitely use a calculator, if at all possible, to do this one. Otherwise, you're going to have to take and square each of these values and then add them together. Once again, I mentioned this once before, but there are 4 columns of numbers here, but you have to enter them all into the same list. because this is just one list of data that we're working with. So you'll have a very long list of data. It will include all of those numbers, and I'm giving you some shortcuts or some hints here. When you do stat 1 and you look at one variable statistics, you should be given all of this, including the range would be given to you. And then it will have the maximum value x and I think the maximum value and the minimum value is given to you, and you calculate the range for this one. You'll also have to find the mode yourself. So you'll have to look at your data and see what the mode is of that, because it doesn't really tell you. One way you might want to do that is look up how to sort the data in your list on your calculator, because there is a way to sort the data, sort in ascending order, and then that will easily help you identify the mode. The next 2 pages in your guided notes are just summaries of the various formulas that we've gone over so far. I've given you ungrouped data, which we've been working with, and I've given you sort of a formula page. You might want to put a tab in this one so that you can get back to it. It gives you the formula for the variance and for the standard deviation for ungrouped data. And the next page, page 19, is what we're going to talk about next. It is the same thing, but it's the formula for grouped data. Now, when we're dealing with grouped data, there's another field that we have to talk about, and it's M, the midpoint. Guys, memorize all of these symbols. Are going to be very important to you, that you know what population variance is, population standard deviation. So these symbols are going to be important. Start using them when you're writing your formulas or your problems, and start naming them when you talk about them, when you go over the problems. 2 things that you need to note before we leave the topic of variance and standard deviation, or we go on into our next discussion of it, is that 1, the values of the variance and the standard deviation are never negative. You're never going to come up with a negative variance or a negative standard deviation. The numerator in the formula for the variance should never give you a negative value. Usually the values are positive, but if a data set has no variation, then that variance and standard deviation are both 0. The measurement units, the second point I want to make, are always the square of the measurement units of the original data. Now this is for variance. And this is because what we do is we square these values, original values, to calculate the variance. When we square these measurements, they don't really make a lot of sense to us. The standard deviation is obtained by taking the square root of the variance, and now we're back to the original units of measure. So the standard deviation, when you get it, is in the same units of the problem. If you were dealing with dollars in the beginning, the problem's dealing with dollars, then your standard deviation is going to be dollars. If you're dealing with age, then your standard deviation is going to be years. It is the same unit as the problem. Now let's talk about calculating the mean, the variance, and the standard deviation for grouped data. Now remember what grouped data is. We've grouped this data, we've thrown it into groups, so we've lost the individual data values. We don't know what they are. So how do you find the average when you don't know what the individual data items are? I mean, we know that there are 15 items that are in a group that's, maybe age 10 to 20, but we don't know the individual values or the individual ages anymore. We can, however, get the best estimate by finding the center of the group and using the frequency of that group to calculate it. So you have some new calculations, new formulas for mean of population and sample data. Now, they're basically the same formula. We just use different symbols to help us remember that we're dealing with population or sample data. What we do is we sum the midpoint of each group times the frequency. That's the middle of the group, whatever the middle value would be in our group, times however many are in that group. That's the frequency. And we take that summation and then we divide it by either the number in the population or the number in the sample. Now, let's take a look at just a really simple example here. I've got a class of students, Professor Blunt's statistics class, and the last test grades are shown here. And he grouped the test grades. He grouped them into intervals. Now, his groups are 50.5 to 56.5, then it goes from 56.5 to 62, and you'll see how his groups go together. And then he listed he counted the number of students that fell into each group. But how does he get the average test grade now? Because he lost all of his individual test grades when he did that. Well, what Professor Blunt has to do is find the midpoint of his group. So for that first group, he would have to get the midpoint by saying, I want to take that lower limit and add it to the upper limit. I want to take 50.5, add it to 56.5, and divide that by 2. When I do that calculation, I come up with a midpoint of 53.5. So I could say, okay, that's sort of where all of those that fell into that first group, there's only one, so I can sort of estimate that that test grade was around 53.5. That's my midpoint. My frequency is the number that were in the group, or 1. I can do the same thing with the next group. I take the lower and the upper limits. I say 56.5, and I add 62.5, and then I divide that by 2. I come up with 59.5. Take a minute and check my math here and make sure I've done these correctly, and practice finding the midpoints and see if you can make your line these midpoints up with these groups. But you can see Professor Blunt's problem. Now he wants to know the average test grade for his class, and he basically lost his raw data. He doesn't know what that score of that one student that's between 50.5 and 56.5, he doesn't know what that score actually was. So all he can do is find the middle of the group, which takes the lower limit, adds the upper limit to it, and divides by 2. That's how we're finding the middle of the group. And he can say, I'm estimating that that test grade was about 53.5. There was one student in that class, so the midpoint times the frequency of the one student would give me 53.5. I'm going to calculate the mean using my formula for the mean for grouped data. So I need midpoint times frequency. Now he's found the midpoint of each of these groups. Now the way he's done it, he's taken the lower limit, added the upper limit, and divided by 2. And that's the middle of the group. So I've done that for you. And then I've gone over here and I've written down how many were in each group for you. All you need to do now is say midpoint times the frequency. Now the number of students in each group, that's the frequency. So we're going to say midpoint times frequency, and once we have those numbers, we will sum them and divide them by n. Now n is equal to the total frequency. The sum of the frequencies is equal to n is equal to, and you'll sum these numbers to see how many students were actually in Professor Blunt's class. And that's what you'll divide by. Go ahead and complete this page and then check back to see if your answers are correct. Hopefully you've done this work by now and you're checking your answers. The sum of the frequencies, in other words, the population n, the number in this population is 19. Now we're saying population because this is all of the students in Professor Blunt's class. So this is everybody. That would be a population number. When I take midpoints times frequency and I add those numbers together, I get 1460.5. And I divide that number by the number in the population, the sum of the frequencies are n, and I get an average test grade of 76 and I just put 5 decimal places. Normally you'll be asked to round to 2 or 3 decimal places. Now let's talk about the variance and the standard deviation for grouped data. We're going to see, I'm only going to give you these shortcut formulas for variance and standard deviation. And you recall, we don't know what the data is anymore, so we have to deal with the midpoints and the frequencies. So what we do is we say the sum of the midpoint squared times the frequency minus the sum of the midpoint times frequency, and we square that number. We either divide it by, and then we divide that by the number in the population or the number in the sample, and then once again we have to adjust if we're dealing with sample data, and we divide the subtraction, the number that we just subtracted, by n minus 1 or n if it's population data. How do you get the variance from there? I mean the standard deviation from there? Well, it's easy. It's the same situation. We take the square root of the variance to get the standard deviation. And of course, this would be your formula for taking the square root of the variance to get your standard deviation. Now, I've given you an example here, and I've actually worked out all the numbers and given you the details so that if you're trying to get back to it, you can always go to page 22. You have this chart on the bottom, and you can see how to calculate the variance and the standard deviation for grouped data. The groups are the daily commuting times in this data, and it goes from 0 to 15, 15 to 30, 30 to 45, and so on. The frequency is listed next, and that's the number of people or commuters that fell into each of those groups of commuting times. Then we would calculate the midpoints by once again taking the upper and lower limits of the groups. You would add them together and divide by 2, and I've calculated those midpoints for you. Next, it's easy. I multiply midpoints times frequency, and then I have to square the midpoint and multiply it times the frequency. I have to sum those two columns, and finally I have enough summations to enter my variance formula. I say the sum of midpoint squared frequency minus the sum of midpoint frequency squared divided by n, and I divide the entire thing by n for population data, or n minus 1 if this was sample data. How do I get the the standard deviation from there? I simply take the square root of the variance number. Now it's time to practice. This on page 23 is an on-your-own activity. The commuting time actually is given to you in these groups, and what you're going to want to do is calculate the variance and the standard deviation, and I have given you a page to work with. A chart is at the bottom. Now, when you're filling in the class is the same as the group. I would say class is 0 to 10. The second class would be 10 to 20. This will make things simpler for you. And then you're going to come up with the midpoints, and you're going to calculate the frequencies, of course, are written here. I'll just get this started for you. The midpoint would be 0 plus 10 divided by 2. So 10 divided by 2, midpoint of this one's going to give you 5. And then, of course, from there on, just follow the things that you know to do for calculating the midpoint frequency and the midpoint squared times frequency. Once again, follow the formulas that are written for you at the bottom of the page and calculate the variance and the standard deviation for this data. Because we've been working with population data, and I want you to get a chance to try your hand at sample data, I've given you another on your own activity on the page 24. Now this is a sample of 525 college students. Note sample, so you're going to have to use your sample formulas when you do this one. These are your groups, so it's going to be 0 to 3.5, 3.5 to 7 is what you can use, and these are your frequencies. Calculate the standard deviation, the mean, the variance, and the standard deviation for this sample of data. The next descriptive measurements we need to talk about are called measures of position. Now, this is where things reside in the data set. I want you to note, before we get started, that measures of position always mean that the data has to be ranked first. In other words, it has to be ordered from the smallest to the largest. So if your data set is not ranked or ordered from smallest to largest, that's your first step. You have to do that, or measures of position make no sense. There are two specific measures of position we're going to talk about. One is quartiles. Now, quartiles divide this ordered data set into 4 pieces. There are only, however, 3 quartiles, because you would have 3 dividing lines to divide something into 4 pieces. You would have split it in the middle, and then you would split those 2 halves in half again. Think about taking a piece of paper and dividing it into 4 equal pieces. You're only going to have 3 cuts in that piece of paper. Percentiles divide an ordered data set into 100 pieces. Now, if you're going to have 100 pieces, you're also going to have how many cuts? Well, it would be 1 less than 100, or 99. So what do we talk about when we talk about percentiles? Because we quite often have a data set that doesn't have 100 pieces in it, doesn't have 100 different data items. We have to do some calculations for percentiles, and we'll use the same type of formula for quartiles. It'll make things easier that way. I want to talk about percentiles first. What we usually have is the question of finding the certain percentile. You'll be asked for the 70th percentile or the 50th percentile, and we use K to represent the percentile that is desired. So K would equal either 70 or 35 or 90 or whatever percentile we're interested in. Now I is the index. That's the ranking position of the data value when, of course, this is a ranked data set. It's already in order. So I is what we consider the term, the individual term, we would count over to the ith member, we would count over to the 5th member or the 6th member of a data set. And n is the total number of items in our data set, just like before. So what are your steps? Well, first you rank the data. You put it from the smallest to the largest, put it in order. And then you calculate the term that you're interested in. You say I is equal to k divided by 100 times n plus 1. Now, if I is a whole number, then the kth percentile is the data value in that position of the ordered data set. But if it's not a whole number, then we have to do is we have to round it up and down to the nearest whole numbers, and then we take the average of these two values. It's a little bit confusing to say it, but we'll do an example that'll make it clear. Now, how do you find something called the percentile rank? If you're asked to find the percentile rank of a certain observation, well, you first, of course, rank the data, and then you let x equal the number of values that are less than the observation that you're interested in, and y is the frequency of those observations that you have. And then you just plug it into a little formula where a is equal to the x value times 0.5 times the y value divided by n, and then you multiply that times 100%. Once again, we'll do an example that'll help you with this. Before we start doing the actual calculations for percentiles, though, let's take a look at quartiles and what we call the interquartile range. Now, like we said before, quartiles are 3 summary measures that divide a ranked data set into 4 equal parts. The second quartile is the same as the median of the data set. So you've already calculated the median of a data set, and that's always what you do first if you're trying to calculate quartiles. You find the middle of the data set. And then you look for the first quartile. The first quartile is the value of the middle term that's always the ones that are less than the median. So we take that first half of the data set and we split it in 2, and that finds the middle term is our first quartile. We do the same thing with the second half of the data set, and that gives us our third quartile. Now, once we've done that, we see that each portion of our data set is divided into 25% of the observations in each section between the quartiles. Now we have one more calculation that we perform with quartiles. We look at something called the interquartile range. Now that's the distance between quartile 3 and quartile 1, the middle half of your data set, if you will. So what do? We take quartile 3 and we subtract quartile 1, and it gives us that interquartile range. Now take a look on the bottom of Guided Notes, page 26. I've written this out for you so you have a really good example to go by, and I've done the calculations there, but you might want to make some extra notes. What I've done is I've listed 20 ages of Academy Award-winning Best Actors, and they've already been ranked. Notice that the data set is set up from smallest to largest. I want to find the values of the 3 quartiles. So the first thing I have to do, and I'm using my formula that was given to me on that previous page that we were working with. I believe that's page 25. So I'm going to take my formula for quartiles, and I'm going to say I is equal to k divided by 4 times n plus 1, and I'm going to go rounding up and rounding down, and I'm going to find the values of that. So when I'm looking for my first quartile, I'm looking for k equals 1. That's the quartile I'm interested in. And so I say it's 1 divided by 4 times how many values are in my data set? Well, there are 20 items, 20 ages. 20 plus 1, and once I do those calculations, I come up with 5.25. So 5.25, if I go down, I'm looking at the 5th term, and if I go up, I'm looking at the 6th term. So I count over in my data set. I want the 5th and 6th term. 1, 2, 3, 4, 5. It's going to be 31. It's going to be, wait a minute, 1, 2, 3, 4. There it is, 30. And 31 gives me the 5th and the 6th terms. So I take 30 plus 31, divide it by 2, and I come up with quartile 1 is 30.5. It really falls right between 30 and 31. Quartile 1, I'm sorry. Now let's do the same thing for quartile 2. Now I would have normally done quartile 2 first because it's the median, but with this formula you can do it any way you want to. And it works the same way. I take k, which is now 2, because that's the quartile I'm interested in, divide it by 4 and multiply it times 20 plus 1, or 21, and I come up with 10.5. So the terms I'm interested in my data set are the 10th and 11th term. So I count them over, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm dealing with 47, and 55. That's term 10, term 11. Take those and add them together, divide by 2, and my quartile 2, which is also my median, is 51. That would 51 would split my data set exactly in half. I'm going to go down here and I'm going to say, okay, what's quartile 3? Well, I use 3 for K and do the same calculations again. I come up with 15.75. Well, when I go down, I get 15. When I go up, I get 16. I'm between the 15th and 16th terms. So when I count over, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's 69 and 71. Add those together, divide by 2, and my quartile 3 value is 70. Let's look at a percentile example and activity together, and it's on page 27. It lists those 20 ages for the Academy Award-winning actors from smallest to largest, and it starts at 21, and you can see, so the data set's already been ranked, and it says to me, find the 70th percentile. Now, I've already written this out for you so you can have a good example to go by. The formula, of course, I'm using is the same one that was on page 25 before. I'm looking at it saying the percentile formula is I is equal to K divided by 100, not 4 this time because this is not quartiles, it's percentiles, times N plus 1. So basically I'm doing the same thing I did for quartiles. I'm just using a different formula. I'm dividing by 100. And when I do that, I'm interested in the 70th percentile, and I have 20 items, and I come up with 14.7. So I go down to number 14 and up to number 15, and those are the two values that I want to add together and divide by 2. When I look for the 14th item, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I find it 64. The next one, the 15th, would be 69. So I'll take 64 plus 69, divide by 2, and I come up with 66.5. You might want to take a minute and do the math and do the formula yourself and make sure you understand how to get the percentile. Like I said, it's just like we did the quartiles. The only difference, we divide by 100 instead of 4. Now that gives me the 70th percentile. The 70th percentile is 66.5. In other words, 70% of my data falls below the number 66.5, and that's the way we interpret percentiles, is 70% are below whatever that number is. So now we want to do another example. We want to find the 83rd percentile. I want you to take a minute and do the exact same thing, but use 83 as your value for K, and see if you can come up with the 83rd percentile before you start the tape back. Now I would use the formula, and I always write formulas down when I'm using them. It's equal to K divided by 100 times N plus 1. That's how I'm going to find the terms that I'm dealing with. And that's going to fill in to be, of course, 83 for K divided by 100 times 20 plus 1. So I'll say that's times 21. I can take that really quickly in my calculator, and I find out it's 17.43. So I'm going to deal with the 17th term and the 18th term, okay? The 17th term and the 18th term. So I count my data items, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 is 73, and 18 is 74. So I say 73 plus 74, and I'll take that and divide it by 2 when I get it. So I'll say 73 plus 74 divided by 2, and this is going to equal 73.5. Well, you can easily tell that halfway between those two, right? So the 83rd percentile is 73.5. 83% of the data falls below 73.5. Now they want to know something else. They want to know, where does 47 fall in relation to the 3 quartiles? Well, that means I've got to find the 3 quartiles in my data set. Now, if you want to go back to the previous page, you can find that data, but you should be able to calculate these quartiles, but I'm going to write them down for you here. Quartile 1 is, of course, equal to 30.5. We did it on the previous page. Quartile 2, which is the median, is equal to 51. And quartile 3 is equal to 70. So where is 47 in relation to the 3 quartiles? Well, really, it's just below quartile 2, and that's really how we would explain it. It's below quartile 2, it's in the second quarter of the data set. If we were to divide this into quartiles, we would come up here and draw some dividing lines. Where's the median? 51 is my median, well, it's right here. So I've split it in half, and 30.5 is going to come right about here, and then 70 is going to go right here. So where is 47 in relation? Well, it's right here. It's in the second quarter of my data set. It's just below the second quartile, or just below the median. Now, what is my interquartile range? Well, the interquartile range, erase this thing so you can see it. The interquartile range is also always equal to quartile 3 minus quartile 1. So that's going to be 70 minus 30.5, or 39.5. That's the distance between the two quartiles. On page 28, I've given you a quartile and percentile activity to do on your own, and I've given you a data set. Please note that it is not ranked, so the first step you're going to have to take is going to be to rank this data set. And then I want you to calculate the three quartiles, the interquartile range, and tell me where 5 comes in relation to those three. Then find the value of the 25th percentile. We'll use the formulas we've already used for that, and give me a brief interpretation. Exactly what would that mean? You're going to be saying that a certain percentage of the data falls below a certain value. That's the interpretation we use, right? And now I want to go to part C. Now, we haven't really done an example with part C, finding what we call percentile rank, so I really want to take you through this one. Let's go back to page 25 and note that at the bottom of the page there is a strategy for finding percentile rank of an observation. The first thing you do is rank the data set, and then you let X be the number of values that are less than whatever you're looking for, and Y is the frequency of that particular value. And then you have a percentile rank formula to use. So I'm going to take you through this one, and the first thing I have to do when I do this is to rank my data set. I'm going to kind of make this a little easy for you, because I'm going to rank a data set that you have here, and I'll write it down here so we can work together. I find that I have 2s are the lowest numbers. There are 2 of them. There are 2 3s. Then there's a 4, 2 5s, 2 6s, 2 8s, and 2 9s. Now, let's see if I've done this right. I've got 2, 4, 6, 8, 10, 12, 13. I'm sorry, I'm not finished yet, am I? I've got 2 10s and 2 11s, and I've got 2 12s, and I've got an 18. Okay, now I think I got them all. Let's count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So I've got 20 items, and it's in ranked order, and I want the percentile rank of 10. So after I've ranked the data set, the second step is to say, what is X? Well, X is going to be the number, according to my formula that I was using, the number of values less than the one I'm interested in. So this is the number of values that are less than 10. That's this thing I have to do next. Well, the number of values that are less than 10, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 13 of them. So that's going to be my value for X. What's Y going to be? Well, Y said it's the frequency of 10. The number I'm interested in is what they're calling A in your formula, so it's the frequency of 10. How many 10s do you have? Well, there are only 2 of them. Now, here's your formula for percentile rank. You're going to say the percentile rank of 10 is going to equal that X value, which is 13, plus 0.5 times the Y value, which is 2, all divided by the number of items in the data set, which is 20, and then we will multiply this times 100%. Okay, all of that will have to be multiplied times 100%. So we do the math. Now, be careful. I would do the numerator first, and then say divided by 20. And then I would say times 100, and then percent. You could add a percent sign there, and you should come up with 70%. So what do we mean? Well, 10 is approximately, 70% of the data items fall below that number 10 is what that means. That's the percentile rank of 10. Now, the last thing we're going to talk about, and the last graphical representation of data I've got to show you, is a box plot. It's also called a box and whisker plot. This gives us a good image of where the data is concentrated in our data set, and it also will identify some extreme values. One of the nice things about a box and whisker plot is that it will identify outliers in your data set. So this box plot is constructed from 5 different values, basically. We have the smallest value, the minimum value that's in the data set, and then we have the quartiles, the first quartile, the second one, and the third one, and then we have the maximum value that's in the data set. And you can see how they would be charted if you were looking at a number line, and the box there represents the middle 50% of the data are inside that box, and of course the line is drawn where the median is, or the second quartile. Now the whiskers go past that 50% of the data, and they show us where the largest and the smallest data values are. It's a really good, quick picture of the data, and it also will show the skewness of our data. So that's one reason we use it. Another reason is it does do a good job of identifying outliers. I want to show you a really quick way to do a box plot with your graphing calculator, and I'm going to do this quickly because not all of you have STA2023 calculators, and that's what I'm demonstrating with. But you should be able to find out how to do a box plot with any of your graphing calculators by just typing that into Google. I've given you heights of 40 students in a statistics class, and I've been asked to do a box plot with this data. Now I've put some pretty detailed directions here for you on page 30, and it gives those 40 students of the statistics class, and actually the data has been ranked, but it wouldn't matter because you can enter it into a list. And I said to enter it into list 1, but it really doesn't matter. We're going to find the minimum, maximum, and the quartiles by just putting them in a list, and I've actually entered mine into list 3. But I'll just show you here if I can. What I do is I say stat and edit, and there are my list. And of course I've already gone ahead and put these 40 values in list 3. I think you can see it. Maybe you can't see it. It's hard to see. Let's see if I can get the visual here for you. Okay, that turned out better. So I've put everything into list 3, and they're all 40 values are there. And now if I want to get the statistics that it's asking me for here, the largest, the smallest, and the quartiles, I'll just do the same thing I've been doing. I'll go stat, and I'll come over to calc, and I'll do one variable statistics, and then I need to tell it list 3. Now this is not grouped data, so there's no frequency list here, but I go down and I say calculate. It comes up with some other things that I don't really need this time, so let me just scroll down until it just has on here what I need. I need the smallest value, that would be the minimum value, well 59 is the smallest. The largest there is the max value, or 77. And then it also calculated my quartiles for me. I have the first quartile is 64.5. The second one, which is also the median, is 66. And the third one is 70. So that tells me my quartiles, and that's kind of nice to know. If I'm doing a box plot, I definitely have to know that. The calculator, however, will do the box plot for me. So, and this is a little bit difficult sometimes, but I think you can probably figure it out in your with your calculator. I've given you, like I said, the STA2023 instructions right here. First, you get the data entered. Mine is not in list 1, it's in list 3. But now I need to go and turn on stat plot. So stat plot, if you can see it, is written in blue. It's right above this button here. So it's written in blue, so I have to press the blue button, and I go stat plot. And I want to turn on a plot, and this one has really already been turned on, but I'm just going to choose that first plot to work with. And then it's on already. I'm going to come down next and say, which plot do I want to work with? Now I'm going to choose, there are really 2 that are box plots. This one is a box plot, and that one is. And the first one will actually show me outliers if I use it, and so that's the one I'm going to turn on. Mine had already been turned on, but you would click on it. And then you would come down and say, where are your data values? Well, they're in list 3 is where I put them. You can also put the frequency list. It's going to want 2 lists for you, so just go ahead and put both of them the same. And then it asks you what symbol you want to use, and you can play around with that if you want to. I just chose the square, and blue is fine for me working with it. And the next thing I want to do to view it is to go to zoom. Now zoom is right here. This middle button says zoom. So I'm going to go to zoom, and I'm going to go all the way down to number 9, which is zoom stat. I could have just typed in the number 9, but I did it this way. And it took that list and it created a box plot. It doesn't look like anything. I have to turn on trace so I can see what these numbers actually are. And here's trace. Right up here by zoom is the button that's trace. And trace will actually sort of identify the values. This tells me my minimum value was 59. And if I arrow over, it'll give me the next point that it's plotted. The next point it's plotted was quartile 1, which was 65. Well, close to 65. And then of quartile 2, it's saying is around 67 is the sort of the center of this thing, and then it's plotting 70 as the third quartile, and it's giving me 77 as the maximum. So it's drawn a graph, gotten very close to those quartiles, which is probably what it would do, and it's giving you a good illustration of a box plot. So you can see the skewness of the data. You'd also be able to see if there were some outliers out there in your data set. This concludes our discussion of Chapter 2. It's descriptive data. I've left you with a lot of notes and a lot of things to try, and you've got quite a bit of information inside Chapter 2. But Chapter 2 does conclude Module 1, so you should be taking Chapter 1 and 2, putting the information together, get ready to do the work inside MyOpenMath, and be able to do the reviews before you take the test.